Okay, so I'm going to go over the multiple choice section. This is test 3, not test 2. Test 2 is wrong. It's test 3. This is my first attempt at a video on an iPad, so hopefully it works out well. We'll see how it goes. Okay, so this question is, which alcohol would initially produce the most stable carbocation when going through an acid catalyzed dehydration? So this is asking about what the most stable carbocation would be, specifically when acid catalyzed dehydration. So acid catalyzed dehydration is when we have an alcohol and it has water and heat, so it becomes ROH2 plus. Then that's a good leaving group, so you can make R plus. If it's a primary, it actually won't form a carbocation. So instead of going by E1, after the leaving group leaves, it goes through E1, so you get an alkene. But if you have a primary, then it goes by E2, so no carbocation will form. So the question here is, which would be initially the most stable carbocation? We can eliminate any that are primary, because if this leaving group left, the carbocation would be right there. If this leaving group left, the carbocation would be right there, and this leaving group left, the carbocation would be right there. So all those are primary. We can eliminate those because they won't form the carbocation. It definitely wouldn't be the most stable carbocation. So then we're just deciding between these two, which is the most stable carbocation that would form. And this one we would get carbocation right there, which is tertiary. And on this one, we would get the carbocation right here, which is secondary. It would rearrange to end up looking just like that one. But for now, it doesn't ask about after rearrangement. It asks about initially. So that's why I choose not B. I don't know why I put B. Eliminate B because initially the most stable carbocation would be A. Okay, the next one for the following reaction and conditions determine if it would be SN1, SN2, E1, or E2. So always the first thing I look at this is the nucleophile. And anytime the nucleophile has a metal counterion it could be sodium, it could be potassium, it could be lithium. All these positive counter ions will mean that the O is going to be negative. I've seen some people try to do that also with OH, where they try to, if it's OH, make it CH3O minus H plus, but that's not going to happen here because this is a covalent bond, whereas this is an ionic bond, and that's why it can separate out. Okay, so CH3O minus disassociates into this, so that means it's a strong nucleophile, so it's going to go to the two sides. So if I look at my nucleophile, it's strong, so it's going to be 2, SN2 or E2, SN2 or E2. So primary or secondary is for the leaving group is necessary for E2. I don't know why I keep misspeaking. Primary or secondary leaving group is necessary for SN2. Bulky, nope, not bulky. Narrow is also favored on SN2. Narrow nucleophile. Over here, a bulky nucleophile would be favored, and it can go primary, although typically primary would rather go SN2 unless there's heat. Secondary and tertiary, and heat also favors this side. So I'm going to look at all those things. We know that this is strong and it's also narrow. So because it's narrow, it's going to favor SN2. So now we look at our leaving group. Our leaving group is, we look at the carbon where it's attached, and it has 1, 2, 3 carbons around it. So that means it is tertiary. So our leaving group is tertiary, which means it can't go SN2. So the only option then is E2. So E2 would be the answer. And that's actually the exact same question that you had on a quiz. It didn't seem like a lot of people had fully gotten through that reasoning, so I wanted to test you on it again to see if you could go through that reasoning process. Okay, which product would you expect to obtain from the following SN2 reaction? So it's telling you that it's SN2, so we know that SN2 does backside, we don't have to decide, we know. The SN2 does backside attack, so it inverts stereochemistry, and it'll attack where the leaving group is. So CH3O minus will attack right here where this leaving group is. This leaving group will leave, and you'll get a new product. This is hard to draw, so wish me just, I guess I'll kind of show you the transition state. So as the OCH3 is coming and attacking, the Br is leaving, and the motion of this OCH3 coming in, here sort of shoves down this hydrogen, so the hydrogen sort of goes out. That's the transition state. And then and it still has its CH3 over here. That doesn't get affected at all. So then after the Br fully leaves and the hydrogen comes the rest of the way down, we get our inversion of stereochemistry. So that's just a depiction of why the stereochemistry inverts. So then we have our OCH3 on top, our hydrogen on the bottom, and our other side hasn't changed. And so we know it's not Br2 because the substitution happens. It could be either of these if you just know that the substitution happens, but between these two, this one has the inversion of stereochemistry, so that one wins, so it's B. Okay, next question. By analyzing the starting material and the product, the following reaction is possibly an example of what type of mechanism? So, and then it says, be sure to consider the overall reaction, the stereochemistry, and the regiochemistry. So the first thing I see here is where this bromine was, now we have an N3. So that is a substitution. No alkene is formed, so it can't be E1 or E2. So it has to be a substitution reaction. Between SN1 and SN2 only would produce inversion of stereochemistry. So SN2 would produce this product, but SN1 would also produce its enantiomer, right? So because we have this and its mirror image, two products, only SN1 could be responsible for that. Okay. Which of the following products represents anti-Markovnikov addition of water across a double bond with syn stereochemistry? So, Markovnikov is when the nucleophile goes to the more substituted side. Anti-Markovnikov is when the nucleophile goes to the less substituted side. So the less substituted side is over here. The nucleophile is OH. So this is the less substituted side. There's nothing already there. Oh, how did I do that? I just made it go away. I don't know. Anyway, the less substituted side is over here. And then H adds to the more substituted side. That's anti-Markovnikov. And then I made these both wedges because it's syn. Both wedges is because of syn stereochemistry. So that's what I'm looking for. A CH3 on the dash and the OH on the wedge. So let's see. I'm just going to go through these and say this is syn addition of diols. And you get this with osmium oxide or cold KMNO4. That's just a little bit of bonus info for you. This looks like, okay, so we have our OH and our H, and the CH3 is on this side, so I think this is anti-Markovnikov and syn, so this is a good option. I'm going to check all of them just in case, because sometimes there's multiple, so I'm just in that habit. Okay, so this is syn addition, but it's Markovnikov. So that's not our option because the OH is with the CH3, more substituted, is more nucleophile more substituted. That's Markovnikov. And then this one, we added the OH and the H, but they're, and they are anti-Markovnikov, but they're also anti-stereochemistry. So that's not good because we want them to be the same because it's supposed to be syn stereochemistry. So answer choice B is right. Okay. Question 6, what is the major product for, or products formed when trans 1-bromo 2-methylcyclohexane undergoes dehydrohalogenation? Okay. So I'm just gonna go ahead and make my trans 1-bromo 2-methyl. So immediately I see my, I always start with my leaving group up on cyclohexane just so that it's easy to see if they can go anti to one another. coplanar or coaxial or whatever. So if the BR is up on this one, then the axial adjacent one that's down is a CH3. So it can't form between these two. That's not an option. So the only place that there is an antihydrogen is between these two. So that is one away from the methyl. So the BR can be taken from, let's see, the nucleophile will take the BR from here. This will go here, this will go there. So it doesn't matter if it's Zaitsev or Hoffman because there's literally only one option because there's not an antihydrogen here. It can't take that hydrogen. So that means that looks like this one is the right one. This one would be between the bromo and the methyl. This one is, the bromine was here, so the hydrogen would have to be taken from here, so that's too far away. And this one, your leaving group would have had to be here for that to happen, so that can't work, so the answer is B. Okay, which structure represents E, 1-bromo, 2-methyl-cyclohexene? So I always start by finding hexene. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Okay, so can't eliminate any based on that. This is messy, so I'm going to erase it. So then the next thing I'm going to look at is the position of the methyl group and the bromo and the double bond. So this has the bromo 1 and methyl 2 and double bond 2, so that's a good option. This has the bromo 1, but also the methyl. Oops, I just thought that A went with that. Dang it, I try to get those out of my test, so I'm sorry if that confused you. Bromo 1 and the double bond 1, so that won't work. This one down here has 1, 2, 3, 4, wait, hang on. It has the bromo 1 and the double bond 2, so that will work. And the methyl 2 also. This one has the bromo 1 and the double bond 1, so that won't work. Oh, a dog just came to visit me. Sorry if you can hear his paw. Apparently you can't do that. Okay. And none of these choices is also not right. So from here, let's see. I'm going to, I have to decide if these are E or Z. A different dog just came to visit me. Hold, please. All right, so we eliminated these because the double bond was in the wrong place. Sorry for the interruption. The dogs came in and I ended up pausing it. But this one and this one and this one definitely are all not good. Okay, but because they don't have the double bond or the bromo in the right place. I guess none of these choices is still potentially an option. I don't know why I crossed that out. So then between these two, basically we have to decide if one of them is E, but they definitely are 1-bromo, 2-methyl hex 2E, and we've made sure the rest of that is right. So between this, I'll highlight on this side first, we have to number the priority, and I'll do that in a different color. So both of these are carbon, so carbon weighs the same, so they have the same priority. This is based on the same priority system you learned for R and S. It's called the Kahn-Ingold prelog. I've heard it called the SIP priority system, or KIP. So both of these are carbons, weigh the same. So then you have to look at what they're attached to. So this one's a bromine and a hydrogen, whereas this one's 3 hydrogens. So that bromine is heavier than, the bromine here on this side is heavier than all 3 of these hydrogens. So this left side over here is priority 1, and then this side is priority 2. Now if you look at the other one, you have a hydrogen on one side and a carbon on the other. That's easy, so this is priority 1. So priority 1, if we draw a line right through the middle of the alkene, priority 1 is on the left and right side on either of these. So that means that this is opposite, E for opposite. Okay, so I think A is probably our right answer, but just in case, let's look here. If we're looking at just this side of the, sorry, let me just highlight the one I want to point out. So now we'll start by just looking at just this side on the double bond. And here we have a carbon, and here we have a carbon, and then this is two hydrogens, just like before. Two hydrogens of bromine. This one's three hydrogens. So this is the higher priority on that side. And then over here, the higher priority is the carbon. So these are on the same side, so this is Z. So yeah, answer choice A is our right answer. So none of these choices is not the answer. Okay, next question. Which of these structures shown depicts the most likely carbocation intermediate formed in the hydrohalogenation reaction? So first step is we add a carbocation here, we add hydrogen on this side, and the hydrogen adds to the less substituted side because it's the electrophile, so that means less substituted by Markovnikov. It just makes sense that if we're adding a hydrogen on one side, we'd pick the side where the hydrogen is going to, as this alkene breaks and it forms these two electrons are what form this bond, then it makes sense that the carbocation is going to go to this side where it's more stable. So basically, I kind of want to say that again. I'm out of practice, I guess, doing videos. So if I look at these two electrons, they can make a bond, they're going to make a bond with this hydrogen, right? Either they can make a bond with this hydrogen like this, and the hydrogen goes to the less substituted side, and the carbocation, it forms because these electrons have left this carbon and they've gone to bond to that hydrogen, leaving an absence of electrons on the other carbon. So it's going to leave a carbocation on the other side. If the hydrogen went here, the carbocation would be here. That'd be secondary versus tertiary. Tertiary is more stable. And that's the whole basis behind Markovnikov's rule. And so the hydrogen will add to the position that is going to be more stable. But it definitely has to add across the double bond, so you can immediately eliminate these two, 4 and 5, because it doesn't add across the double bond at all, and 1. All three of these, 1, 4, and 5, don't add across the double bond, so none of those make sense, unless it would go to a rearrangement, but it wouldn't rearrange to something less stable. So then only these two options are left, and this is the electrophile adds to the less substituted side, and so the carbocation is tertiary, or this is the electrophile added to the more substituted side, and the carbocation is secondary. Secondary is less stable, so it's more likely B. Okay, the regiochemistry and stereochemistry in the acid catalyzed hydration of an alkene, so that's exactly what acid catalyzed hydration is with an alkene and H plus. I'm going to make this, it could be any old one. R just means any carbon chain. And H2O, the first step is we get our hydrogen added, and it's going to go to the hydrogen goes to the less substituted, so that our carbocations are the more substituted, and then the water will attack. So that's the mechanism, which helps me explain why then we get the stereochemistry and the regiochemistry that we do. So the carbocation goes to the more substituted place, so it has to be Markovnikov. So we can't have a C or D. And the next step is, are we getting syn, anti, or a mixture? Well, that is, the regiochemistry, or sorry, the stereochemistry, syn, anti, or a mixture refers to how do these add together? Does this hydrogen and this alcohol, are they a wedge and a dash? Is it a dash and a dash? Oh, I accidentally drew a wedge. How are they adding with relation to each other? But because we have this carbocation, carbocations are sp2 hybridized, they're planar, so they're flat. I wish I could show you with my hand, but I can't. But they're flat, so the nucleophile can either attack from the top or it can attack from the bottom if they're totally flat. It can either go as a wedge or as a dash. So you get a mixture, and so you get both syn and anti-stereochemistry. Okay. Identify the major product for the following reaction sequence. So this reaction sequence, I see this and I immediately know this is hydroboration oxidation because hydroboration has a boron, and that's the only boron that we've really seen. And hydroboration oxidation, I know, goes through the mechanism where it forms this basically this complex where we have a BH over here and an H over here. I drew that wrong. An H here because it's BH3. So it's sort of the BH lines up. I guess I'll start from this part. This is a cyclopentane. The BH lines up. I did that wrong again. Where the boron goes to the less substituted side because it's less hindered. It still has its two hydrogens, but you can sort of see how it lined up like this, and then this actually forms a bond. So we get this intermediate here, and then the intermediate breaks, and we get our BH2. Oopsie. Man, I'm really struggling. I didn't sleep enough last night. I took a plane to see my sister, and it was late. That's why. So we get this, and then that's the hydroboration. So that's step one. Step two is replacing that with an alcohol. So we've added our OH and our H. So that means that answer choice E is our right answer. And then just to take it one step further, I'm going to say, how could we get all the rest of these? This we would get B with the H2 and some kind of metal, platinum, palladium, whatever. It just deleted that alkene. This one is addition of an alkene, Markovnikov, but there's no rearrangement because if it the carbocation were to form there, then it would rearrange. So that is oxymercuration, demercuration. This one is acid catalyzed, and I know that because, again, we would have gotten rearrangement. So we added alcohol on one side, H on the other. So all this one, and this one, all three are an addition of water. So based on the three additions of water, you can kind of figure out this one's anti-Markovnikov. So it would have been made with the reagents that we had. This one had rearrangement because the alcohol doesn't add across where the double bond initially was, and this one had no rearrangement. So that's how I tell the difference between those. And then if I just wanted to cleave it, that would be O3 in DMS. Okay, which of the reagents below would, oh, I never circled the right answer. If it's like 1, 2, 3, 4, 5 like this, you can always just assume that those correlate to A, B, C, D. So that would be E. Which of the reagents could convert cyclopentene into cyclopentane? So this is testing both your knowledge of naming and your reaction. And the only way that we've learned to get rid of double bonds completely is with H2 and metal. What is that? Hydrogenation. I don't know why I couldn't think of that. Okay, next question. What is the expected major organic product of the following reaction? So that would be KMNO4 cold. So this is going to add two alcohols across your double bond, and they're going to be syn because they're both attached to that same oxygen on the, is it manganese? I think so, manganese. Yeah, potassium permanganate. Yeah, so I think it is. Okay, so this adds these two syns, so they'll either both be wedges or they'll both be dashes. So this one looks like it cleaved a double bond. That would be with KMNO4 hot because it cleaved the double bond and made it into a carboxylic acid. This would be with MCPBA to make the peroxy acid. This would be osmium oxide in DMS, or I guess you could do, yeah, no, just osmium oxide in DMS. And then let's see, this added our two alcohols, but they're anti, which is not what we want. And this is the only one that adds our two alcohols, syn. Okay, the rate equation for a nucleophilic substitution reaction of a tertiary alkyl chloride with CH3. Okay, so the first thing I look at is our nucleophile is weak. Oh, and it tells me that it's a nucleophilic substitution, so I don't even have to decide between SN1 and E1 because it told me. I know that because it's weak, it's going to favor the ones, and so it's going to be SN1. So this nucleophilic substitution is specifically SN1. I always decide what kind of reaction it will be before I answer these kind of questions, just so that I know, what I'm looking for. So, but I guess if it's SN1 or E1, it doesn't matter because it would be the same either way, which would be, let's see, rate equals the substrate, so that would be the RCl. So that'd be answer choice A. I think somebody emailed me and I might have made a mistake in this in the key. So if I did, I will, like in the actual key, what I graded on. So if I did, I will go and double check that. Okay, and then which alkene would liberate the most heat per mole? So that's the least stable. So less substituted is less stable. Less stable, less substituted. And also between equally substituted, cis is less than trans. So this has one substitution. This has two substitutions. This has two substitutions. Two substitutions and two substitutions, so A would be our right answer. Okay, 15 bonus questions. So the first thing I'm going to do is try to tell what kind of reactions these are. So this first one looks like an elimination based on the fact that there's heat. But if we look at our nucleophile, and you know what? I get this question a lot where it's like, which one of these two would be the nucleophile? And let me ask you what I ask people every time in this is this one strong or weak? Hopefully you answered first, but I'll answer weak. And is this one strong or weak? And this one is strong. And so then I ask, between these two, which would react faster? So I want you to think about that in your mind. Do you think a strong would react faster or a weak would react faster? And then I will answer it for you, is strong will react faster. So if strong is going to react faster, then this will be the thing that reacts first, while the solvent, or the other thing, is just hanging around. So that's why the weak one will act as a solvent. So we have a strong nucleophile, so that is going to favor SN2 or E2. And then with the heat, we make sure that it's E2. So that reaction would be E2. And then the next step is going to be oxidative cleavage, where we cleave our double bond. So the first step is going to be SN2 or E2. So we have two hydrogens here and two hydrogens here. This is our bromine, 1, 2, 3. We also have a hydrogen here. Okay, and this is narrow, so this would give us our most substituted product. So I think, but what's hard about this is we don't know based on stereochemistry if this is anti-coplanar or not. Let me think about that for a second. That's kind of tricky. I think somebody asked me a question about this as well. My instinct was not to go between those, I think for two reasons. One is because if I went, let's see, the stereochemistry on this would be tricksy. We have our bromine here and our hydrogen here. Could a nucleophile take this away, put this here, and make this leave? I guess in theory that would work. I can't think right now of any reason it wouldn't. My answer key that I made originally, I went for the less substituted side just because there was two of them and I thought it'd be more likely. And then I also was like, not sure if that would be anti-coplanar or not. But so the nucleophile will take here, this would fill in, and this would give here. So these are our two kind of options for the elimination. So I guess the thing with site-sev is it would probably go through here, and then that would give us, let's see, let me make sure the numbers on this are right. 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I think A is actually the right answer, but I think on my answer key when I was making it, like for the test, I picked D. So what I'm going to do is I will go back and give points to anyone who answered A or D. I won't take away the points, basically. But both of these would have been wrong. This one's wrong because the alkene right here would cleave like this. And so this would not become an aldehyde. It would just be a double bond oxygen right here. We basically added an extra carbon on that one, so that one's wrong. And this is osmium oxide would do that. You know what? I think I just realized, did I say the wrong thing here? No, I did. I said O3 and DMS. Okay, good. Okay, I'm losing it. I did not get enough sleep last night. So I will give points to anyone who answered A or D on that one. And then same thing here. I think I might have accidentally circled this one just without thinking, like making it the nucleophile, which doesn't make sense. I was making the key in kind of a rush. So same thing on this one. If I'll double check this against my answer key, and if I got this one incorrectly, I will make sure that you get points for both of them. I think those are the only ones that I had questions on. Let me just double check. But if you have any questions on this, or if you're not sure why you got the grade that you did, I will, you can email me and I will address your questions. All right,